Hi grade 12s, this is the last video now on trig equations, and finally we're getting into our grade 12 trig equation examples. Now to be honest, I don't think these are any more difficult than any of the other equations. It's just that in the previous grade 11 equations we only had to worry about grade 11 trig identities, whereas now we need to think of these grade 12 trig identities. So we're looking at things like sine of 2 theta, which is equal to 2 sine theta cos theta. And then we're looking at cos of 2 theta. Obviously there might be other identities as well, but these are the three that we have to think about. Now don't forget that there are three ways to write cos of 2 theta. There's the cos squared theta minus sine squared theta if you're looking for a mixture. If you're looking for only using sine in an equation, you would use that. And if you're looking for using cos as an equation, you'd use that. Now all of those are given to you in the formula sheet, so you don't have to remember them. So we're going to look at two examples. Example 1 is all about looking for something and replacing it with the identity. And then example 2 is going to be looking for the identity and, oh, it sounds confusing, so let's just get into it and then it'll make more sense. Okay, let's look at example 1. So question A says solve for theta and it says cos 2 theta. Now immediately I see cos equals sine, and so I'm like, could this be a tan? Because remember, when there's cos and sine and it's only two terms, it could be a tan. Now the reason why this isn't a tan is that those angles aren't the same, so that's out the window. Could I force this to be a cos equals cos or sine equals sine? And I actually could. The only problem is this is negative sine theta, so there is actually an option here, which means how do I rewrite negative sine theta? Could this be cos? Instead of going 90 minus like we always do, could I go 90 plus theta? Now I think I could, because cos of 90 plus means quadrant 2 and cos is negative. So this would reduce to negative and the name would change to sine theta. So absolutely I could do this using a cos equals cos. If I'd like to avoid that and just to do something different, could I see cos 2 theta and think, why don't I just use the identity? And I could. Which identity? Well, I would think the second one of 1 minus 2 sine squared. Reason being, then I would get this equation to only involving sine squared. So this would be 1 minus 2 sine squared theta equals negative sine theta. So I'd probably take everything to the right hand side just to get a positive coefficient of sine squared. So minus sine theta minus 1. Hopefully it factorizes fairly easily. So 2 sine theta, and I think it's minus 1 plus 1, which means that sine theta is equal to negative a half, or sine theta equals 1. Now we've seen sine theta equals 1 before, because sine theta equals 1 always lands me up with a kind of weird answer because the two answers coincide. Reason being, if you shift sine 1, you get 90 degrees. So your two answers would be 90 degrees and then 180 minus 90 degrees, but that's also 90. So actually there's only one solution for sine theta being equal to 1 in the first 360. So that one is easy. Sine theta equal to negative a half, not a problem. Shift sine negative a half and you get negative 30 degrees. So it's negative 30 plus k 360. And then don't forget that your second solution for sine is 180 minus. So you do 180 minus negative 30, so it'll be 180 plus 30 in the end, which gives me 210 plus k 360 degrees. Now, if you did it the cos equals cos way, you have to land up with these exact same solutions, otherwise we've made a mistake. And so it's quite an interesting exercise to go and solve it this way. Obviously that example would be the plus minus because it's cos equals cos, and you'll get exactly the same answers. Now I just would like to explore that a bit, because sometimes when you do different methods you get what looks like different answers and yet they're the same. So let's just practice this quickly. I'm just going to make a separate bubble here. If you had a cos equals cos, either your angles could be equal, so 2 theta would equal to 90 plus theta plus k 360. K is an integer, so I'm not going to bother writing it. If I minus theta on both sides, I get theta equals to 90 plus k 360. Which matches that, so that's good. Or don't forget you could have the negative angle. So you could say negative 2 theta equals 90 plus theta. Now I could have said 2 theta equals negative 90 plus theta. It doesn't matter where you put the negative, as long as there's a negative on one side. Now what that would be is negative 3 theta would equal to 90 plus k 360, and if I divide it by 3, I'd get negative 30 minus or plus, it doesn't matter, minus k 120. Now this is where, if you did it this method and you looked at a memo and you got that, you would say, well, that's not the same as that, and then you'd think you're wrong. So always just be careful. Check if you develop the same, you generate the same solutions. So far these two matched, so that's good. Now let's check the other two. If I just have a look at this, these answers, if I wrote them out, that would be negative 30. Now if I added 360, I would get to 330. Okay, 210 is also an answer. If I subtracted 360 from 210, so 210 minus 360, I'd get negative 150. So those are the types of solutions you're generating. Now let's look at this answer here. So negative 30 seems right, so that's generating that. But where did the 210 disappear to? Now it hasn't disappeared, because if you say negative 30 and you add 120, guess what? You generate 90. Now you might look and like, but that's not on this list. Now it's not, but it's on this list. So 90 is actually, and there it is there, 90 is a solution. If I add another 120 to that, guess what? I get 210. So this negative 30 generates the 210, which is the second solution. So they look completely different, and yet if you generated the first couple of solutions by just adding 120, you would get the same set of solutions. So I just really encourage you to never look at a trig equation memo and think, oh, I did it incorrectly. There's lots of ways to write what actually is the same sequence of answers. What a cool example. That was fun. Okay, so that was interesting. Let's look at B. Another 2 theta 1. Now the only difference here is this is 3 terms. So this is a mixture, but there's no ways that this can be a tan or a cos equals cos, because there's 3 terms. So preferably, I think I'm going to get rid of that and hopefully get everything in terms of sine theta, and this will probably end up being a trinomial again. So you do start noticing that these start getting quite predictable. So if I bring this over to this side, it's 2 sine squared theta plus 3 sine theta minus 2. Don't forget you can substitute in an a if you prefer not to factorize with sine theta, but it isn't too bad. So correct me if I'm wrong, but I think it's plus 2 minus 1, because that'll make 4 sine theta. Yep, that'll work out. So I'll end up getting sine theta equals a half, or I'll end up getting sine theta equals negative 2. Now this happens a lot. In equations, we don't have hundreds of marks to give away. So to create a trinomial that then lands you having to solve 2 trig equations where you're actually testing the same concept twice seems a bit of a waste. And so often what will happen is that you'll get one of the solutions that actually can't possibly work. We should know that the value of sine theta and cos theta range between negative 1 and 1. Tan theta can be anything, but not sine and cos theta. So that is not possible. If you shift sine to negative 2, you would get an error, and that's when you must go, hang on one moment, there's something wrong. Now this one's pretty easy, because the inverse of a half, you get to 30 degrees, so it's 30 plus k 360. We get used to that special angle. And the second answer for sine is 180 minus. So 180 minus 30 is 150. And so there's actually 2 solutions for this equation. Right, that was a nice one. Let's have a look at question C. Oh, this is interesting, because there's a sine 2 theta and a cos 2 theta. So immediately I thought maybe a tan. The only problem is I can't do a tan because there's a third term. If that third term wasn't there, I could hopefully get this to tan of 2 theta. Now this is a really nifty question, because there is no option for sine 2 theta except for minus 2 sine theta cos theta. So I am forced to take a mixture there in the middle term. Now, if I'm forced to take a mixture in the middle term, it might be a good idea for me to choose a mixture in this first term. Reason being, I've said this before, if you can't beat them, join them. If you're forced to have a mixture, then make everything a mixture, because it might be one of those trinomials where you have sine and cos in both brackets. Don't forget that if it doesn't work out, you just start again. So because I have a mixture in the second term, I'm going to change the cos to theta to cos squared minus sine squared. Sorry, I had to squeeze that in. Now this 1, I'm not happy with this 1 either, because I can't have a constant that isn't a mixture, because then it won't factorize. If you're going to have a mixture, then every term has to have a trig ratio. So I think I'm going to have to change this to cos squared plus sine squared, simply so that everything is a trig ratio. We'll have a look in a moment when we get to the trinomial and see why that was important. So if I have just multiply this in now, this is 3 cos squared minus a cos squared. So I'm being quite naughty by just skipping some steps here. And then minus 3 sine squared minus the sine squared is minus 4 sine squared. And then minus 2 sine theta cos theta. Now this isn't written in a particularly user-friendly way, so let me rather write it as a trinomial. The cos squared, then the mixture will be in the middle, 2 sine theta cos theta, and then the sine squared. Now this is exactly what I foresaw happening, which is why I removed the 1. If you didn't remove the 1, if you kept this as 1, you would have some sine squareds and some cos squareds, and a mixture, and then a 1. Now that would be 4 terms. I can't possibly have that. And so to force some like terms to get it to a trinomial, I changed the 1. Now, on my question paper, I would probably factorize this, simply because it's easier to factorize that, and then I would just go and replace the sines and coses. I'd probably do this red on my question paper because I don't have to write it down. So 2a would be times a. Now let's ignore the b's for now. So if I erase these b's for now and just pretend they didn't exist, immediately I'm seeing my error. I should have taken out a highest common factor first. Might make my life a lot easier. So this would be a squared minus a minus 2. So this would be then a, and I'm going to think it should be minus 2 and plus 1. Now don't forget there were meant to be b's here. There was meant to be a b and there was meant to be a b squared. So what that means is that this is a b and this is a b. Now all of that I probably would have done on my... You can do it in your exam. It's just that then you have to say let cos theta equal a and let sin theta equal b. Whereas I prefer to do that on my question paper. on my question paper, and then on my answers I go straight to the fact that I know that this is cos theta plus sin theta, and this is cos theta minus 2 sin theta, because I'm just replacing the a's and b's. Now let's just check. It's always good to check. That would be cos squared. Now forget the 2 because that's highest common factor, so that's okay. This would be minus 2 sin theta cos theta plus, so that would be minus one of them. But I've got the 2, so that's minus 2. And then this would be minus 2 sin squared, but times the 2, so it'll be minus 4. So actually it is right. Now this is a lovely question to ask, because basically this 2 can never be 0, so that's not a factor. But cos theta plus sin theta could equal 0, or cos theta minus 2 sin theta could equal 0. Now this is going to probably land up with 2 tan equations, because I'm quite used to these now. It's 2 terms, it's sine and cos are the same thing. So I would say sin theta equals negative cos theta. I would divide by cos theta, and I'll get tan theta equals negative 1. Or if I change this to cos theta equals 2 sin theta, if I divide by cos theta on both sides, I get 2 tan theta. So I get tan theta is a half. So I've run out of a little space here, so I'm afraid I'm going to continue below. Fortunately, tan is such a nice equation. Shift tan of -1, and I get -45. So it's -45 degrees plus 180k, or k 180. K is an element of integers. Or, if I shift tan a half, that is equal to 26. So, or theta from this one here, theta is equal to 26,57 degrees plus k 180. K is an element of integers. So that is a hugely mean question, because both double angles and you had to pick the mixtures and factorize a trinomial. Fortunately, they were both tan, so that was just a little bit easy. But really, really nasty question there, I must say. Fun, just a little bit nasty. Okay, now I've erased all of that, so we can start with question D. Let's have a look. There's cos 2 theta. There's cos 2 theta. Oh, don't want that, because there's some sine squared. Oh, there's a cos theta. This is fascinating. So now, what do? I've got a mixture. I've got sine squareds, I've got cos theta. It's kind of a conundrum. Do I go to a mixture because I've got some sine squareds? Now, if I have a look at this, here's a constant. Now, that's 6. I could change 6 to sine, 6 lots of sine squareds plus cos squareds, but that seems a mission. So the key to this lies in the fact that there is a cos theta. Now that's not a mixture. In the previous example, if you go have a look up here, this middle term was a mixture. So I was thinking, cool, mixture. This cos theta here is not a mixture. Now there's no ways I can have a cos theta term, if this is going to be some trinomial. If it's going to be able to factorize, I can't have a cos theta. I either need a cos squared or I need a sine cos mixture. So the moment I see that cos by itself, I'm like, I think, can I get everything to cos? If I can get everything to cos, of course if I can't, I'm going to come back and try again. But, sine squared can go. That's not a problem. Sine squared can change to cos squared. Cos theta can't change. So let's try. Let's try take everything and get it in terms of cos and see if it works. Now, what that would mean is I'm going to change sine squared to 1 minus cos squared. Now, the moment I do that, I kind of think that this is going to work out. So even though this looked like it might be a mixture, the reality is I see the cos theta by itself and I'm thinking, can I get everything to cos? So changed cos 2 theta and changed sine squared. So a little bit messy now, so let's neaten it up a bit. So 2 cos squared theta minus 1 plus 6 equals 4 minus 4 cos squared theta plus 5 cos theta. So get everything to one side. So this is now 6 cos squared theta minus 5 cos theta. And minus 1 plus 6 is 5. 5 take away 4 is 1. So hopefully this can factorize fairly easily. So 6 cos theta times cos theta. I think it has to be minus 1 plus 1, which makes me a little nervous because I know that that's not going to factorize. So let me just check. 6 cos squared, so minus 6. Now this is a problem because positive 1 times negative 1 will be a negative 1. So I've got to go back and make sure that I haven't made a mistake somewhere. Right, I found my mistake. I was just assuming, for who knows why, that the only way to multiply together to give me 6 is 6 and 1, which is completely not true. So let's erase this. I just launched into 6 and 1 because I saw the 5, and that's dangerous because the second option would be not cos squared, so it would be 3 and 2. So what happens if I did 3 cos theta times 2 cos theta, and then these could both be negative because then I'd get the 5 in the middle. So that was a bit poor. Anyway, it lands you up with the fact that cos theta could equal a third, or cos theta could equal a half. Both of those are viable solutions. The good news is that it's very easy to do cos equations because you just do plus or minus, so that's quite nice. So when is cos theta equal to a half? That's its plus or minus 60. That's easy because that's a special angle. So plus k 360. K is an element of integers. And then shift cos of a third. theta is equal to 70, 53. 70, 53 plus or minus, my apologies, plus k 360. K is the amount of integers. So that's definitely fairly mean. It lands up in two easy equations, but really nice question, because you could spend a long time wondering which 2 theta ratio to go to. So these are definitely examples of the more you practice, the better you get. You get used to the way things work. Should you use a mixture, you just be able to read questions a bit better. So trig equations definitely one to practice. Okay, now that whole of question 1 was the idea of seeing somewhere where you can replace something with an identity. Now the whole point of example 2, I'm just going to do 2 quick questions where can you recognize an identity and work the other direction. So what I mean is, have a look at this. Example 2, solve for theta. What happens if you have sine theta cos theta equals a half? Now a mixture of sine theta cos theta equals a half, that's not 2 terms. There's no ways that can be tan. I can't isolate one of those ratios. I can't divide by cos, because then I'll just get a divide by cos on the other side. So I've got to start thinking outside the box. And the moment you see sine and cos together in one term with sine theta cos theta, we should always think sine 2 theta. It doesn't matter if there's not a 2 here, because if you put in a 2, you could just times by a half to cancel out the 2, which we did quite a lot of when we worked with double angles. However, here, even better, what happens if I multiplied both sides by 2, and then I would get 2 sine theta equals 2 sine theta cos theta. So that's even better. Now this is directly sine 2 theta. So you get sine 2 theta equals 1. Don't forget 1 is this wonderful one where you only have one answer. So this is 90 plus k 360. And here they gave us a specific domain they wanted. So they wanted from negative 360 to 360. So, well, it would help if I'd finished the question. Let me just divide by 2 quickly to get plus 45. So this is actually now plus k 180. So there's going to be more answers than I originally thought. So therefore, what would fit into this domain? Well, 45 would fit into this domain. If I added 180, I'd get 225. If I added 180, that would be outside the range. If I subtracted 180, I get minus 135. And if I subtracted another 180, I'll still be within the range at minus 315. It's actually 4 answers. So these ones are quite nice. They actually end up being fairly easy, but you've got to recognize that pattern. Okay, and the last one, I think this will probably be something that you'd pick up quite quickly, because the moment I see this pattern of sine 3 theta times cos 30 minus cos 3 theta sine theta, I'm thinking, this looks like a compound angle. So if this is angle A and this is angle B, then this is angle A and this is angle B. So I'd just go to my formula sheet and I'd look for that pattern. Where is sine of A, cos of B minus, and this is a sine compound angle. And if my memory serves me correctly, this is sine A minus B, if you look at the identities, I hope, at least. So therefore, this would be sine of 3 theta minus 30, because I identified who A and B were equal to minus root 3 over 2. Okay, this isn't too difficult. If I shift sine of negative root 3 over 2, it is actually a special angle. So 3 theta minus 30 degrees will be equal to negative 60 plus k 360. K is an element of integers. Just immediately go and set up the second solution. So or 3 theta minus 30 would be equal to 180 minus 60, which is actually 240. So go and set up that one immediately, because otherwise what most people do is solve for theta and then do 180 minus that. So now I'm just solving my equation. So I'll get 3 theta equals negative 30 by adding 30 to both sides. Then I'm going to divide by 3 and I get negative 10 degrees, and I'm dividing by 3, so it's now plus k 120. K is element of integers. Okay, and this last one, add 30 to both sides, which gives me 270 plus k 360, and again divide by 3. So 270 divided by 3, I get 90. Well, that makes obvious sense. plus k120. K is the element of integers. So yeah, those were just quick short ones. Those are actually really nice equations, but you just got to recognize the pattern. And that's it. That's the end of trig equations. Unfortunately, the reality with trig equations is that maybe they ask two trig equations, and there's so many various options that trig equations can look like. They like to ask trig equations in graph questions. So if you have two graphs, they like to ask you to find the point of intersection, which actually then just becomes a trig equation. So I'm afraid it's a lot of practice for seemingly little reward, because they then only land up asking you two. But don't forget, trig equations can each be worth 6 marks, and that's quite a lot. Okay, well done everyone.